Okay, a few more application. Okay, this for defect inspection. Let me show you some. Okay, this original image. Actually, this image is a solar cell. Okay, the solar image. So you can see the conductive line here. If we go for the opening, okay, go for the opening. Not binary. This is not a binary image. Okay, it's a ground level image. We apply opening with a structural element of 9 by 9. See that? If you, I mean, why we put 9 by 9? That's because the box line here have the width, okay, a little bit smaller than 9 by 9. Okay, so after that, you can see that we can remove all the white line here. But if you, well, it's hard to see. If you take a very close look here, can you see? There's a defect. It's a broken line here. Okay, 它那个线那个导线断，那这个会影响。Okay, it will affect the conductivity. Okay, of the solar cell. 那个太阳能板这里有一个黑的，你们看到？弄完以后呢，那从这里事实上这里看不到，but if you go for the threshold, you can see the difference here. Okay, you can see the difference here. That's one of the application. Okay, and here's another application. Similar, again, it's a solar wafer. You use a bottom hat, okay, or black hat. Okay, again, the structural element is 9 by 9. As you can see here, okay, all the conductive line is broken, right, with some scratch. See that? Okay, and up to bottom hat, what you can get, see that the difference is brighter. Okay, so that's one of the application with morphological operation, but you need to do some combination. Okay, dilation, erosion, open, close, top half, bottom half, etc. Okay. Okay, the similar application, but unless I mean the defect here. Okay, this blemish here is hardly visible. See that? Can you see a little bit of the difference? Okay, could be some of contamination. Okay, then again you apply the bottom half. Okay, structural element is 3 by 3. Okay, but after the threshold, you can see, you can identify this contamination. Okay, that's one of the application. Okay, I will skip some of the here. Actually, this solar cell is made from so-called, let me see how to say it, multi-crystalline. Okay, it's a multi-crystal wafer. Okay, 叫多晶系. Okay, it's not like the IC. Most of the very expensive IC wafer use so-called normal critical. Okay, that's I'm the critical. The crystal is only a single with a single material, but it's multiple crystal. It's cheaper. Okay, the manufacturing cost is cheaper, but you see basically you have a very random, especially for this one here. Okay, can you see that? Okay, it's a crystal gram. It's quite different, okay, from a uniform crystal wafer. So if we want to identify something, if there's something wrong with the crystal, first you can apply. You use a very small 3 by 3, so you can remove the conductive line here, okay, but it retains the box line, okay, retain the box line, appearing the width of the box line is larger than 3 by 3. Okay, larger than 3 by 3. Then you apply opening so that they can remove, okay, the conductive line here. So we can see the background of the multi-crystal line. Okay, so that's one of the another application. But you can see it's not as you have lost some of the fine details because you apply 3 by 3. Okay, because you apply 3 by 3, so you can see some mosaic effect. 那个马赛克效果啊，你要用很大哈，那个马赛克效果会留着啊，在这边。Okay, that's just some of the application. Okay, let me go through it. We spend too much time on it. Okay, this is for texture analysis. I keep saying to apply the morphology, you need some prior knowledge. Okay, for this case, suppose the diameter of the large ball on the right is 35 pixels. Okay, the diameter 直径35. But for the smaller, okay, ball or circle on the left, okay, diameter is 25. Okay, now suppose the background grad level is 100. Okay, and the circular ball has the grad value very close to 0. That's it. Okay, so here's we want try to find the region that will separate these two textures. Okay, one with the larger ball, the other one with the smaller ball. Now let's see how can we do it with morphological operation. First, it applies the dilation. Okay, it applies the dilation. What's dilation? Try to find maximum, the maximum. So for this case here, the background is brighter than the ball, right? Okay, so it applies the dilation. Remember, what is the diameter of the small ball? 25. 25. Okay, the large ball is 35. So it applies the dilation. Okay, 27. So after that, all the small balls are gone. They are gone. Okay, it becomes the background. Okay, and then it applies the opening with the diameter 35, which means you will fill or you will connect all the larger balls together. See that? Okay, and then you do the erosion from here. Okay, you do the erosion. Erosion means what? You find the minimum value. Okay, you find the minimum value. Then you do the subtraction. After that, we do the subtraction for these two images. So what we got is the boundary that separate these two textures. Okay, so here we put the boundary. We superimpose the boundary into the original images. See that? It will show you. Okay, almost a perfect, okay, separation of these two textures. Okay, and this show you again. It also show you the region, okay, or the boundary by using a square structuring element. Okay, for this one, the structural element is a circle. Okay, the structural element is a circle. But for the result here, it becomes a square. Okay, becomes a square. So if we use a square, the boundary, you will see some zigzag, right? A line here. But if you use a circular, okay, structural element, so the separation curve will be more smooth. Okay, it's smoother. Okay, that's it. So this depends on how you apply the morphology. Okay, for your operation. Okay, that's one of the applications. So that's it. Okay, so that's about the It can use a lot. Okay, from the supplementary material, okay, in your Hangout. Okay, you can find it from the portal. It shows you a lot of different application with morphology. Okay, based on the textbook, image processing. Okay, image processing. 好，假如说你看一下，老师有把那个image processing 的那本教科书里面的所有跟 morphology 有关的图，它都附在那个附录上面的。好，补充资料，你可以看它的应用啊，你会很惊讶，它可以做这么多事情啊。OK。Okay, so that's all about morphology. Okay, you can apply that to binary image or ground level image. Okay, even someone talking about how to apply it to color image, but it's out of the scope of it. Okay, have you ever think of if you have if the color. If you have a color f of x, y container R, G, and B, have you ever thought of how to find the maximum? I mean, for dilation, try to find the maximum. How to find the maximum of a color image in a local area. You know, it's almost not possible to define. You know what I'm saying? Okay, but if you are interested, you can look for some paper that talk about how to extend the morphology for color image, but even how to define the maximum value in a neighborhood. Okay, in some neighborhood. That is a problem. Okay, that is a problem. Okay. Okay, our next topic. Anyway, hopefully I can finish the basic machine vision topics. It may not be possible in 2 more weeks. Okay, in 2 more weeks, and then we go for the deep learning. Okay. Deep learning for computer vision, hopefully, okay, because we still have some topic. We need to talk about edge detection, corner detection, Hopf transform, and then texture analysis, okay, the last portion where we take. So hopefully we can finish it in 2 weeks, no more than 3, and then we'll skip to, then we will jump to deep learning. Okay, anyway, next week suppose the midterm exam. Okay, so no midterm exam, no written exam for the class. So we will continue the lecture next week. So please come to the class on time, the same class here. Okay, no written exam. Okay, no written exam, and hopefully I can finish the traditional part in 2 weeks, and then we can go for. And then next, and after that, then we can discuss what about your term project. Okay, your term project. Okay, anyway, let's talk about the edge detection. As I can mention, by looking at the figure here, you know what I'm trying to draw, right? It got to be a house. Nobody will think of it as anything else. I believe so. Okay. So all you see is what? Edges. Edges. Nothing else. No color, no texture, no nothing. Just edges. Which means edges will give you the most important information in an image, okay? So we need to spend some time, a little bit of time to talk about how we detect the edges in an image, okay? course, the edge detection can be applied in a color image or grad level image or anything, but we just stick on grad level image. Even for color image, you can convert it into grad value image, right? Okay, there's a lot of application with edge detection. You can use for feature detection. You can, as I mentioned, edges itself, okay, or the line can be the feature, okay, the very important feature, or we can simply just use the edges for segmentation to segment an image into different region, okay. It can also use for motion analysis. I don't believe we have the time to mention that, but anyway, we focus more about how to extract the edges, okay, and use it as a feature representation. Okay. So first, we need to define what does it mean by edge in image, okay? You can see an ink, and the edges, by definition, in image is nothing but a sharp intensity transition between neighboring pixels. That's it, okay? So, it means what? It means for any pixel point, when you take a look at a pixel point, you want to know if this pixel point is an edges or not. We simply just look for its neighbor and see all the neighbor will have significant intensity changes. The transition, it means from black to white, which means it's quite easy to identify the edges from a very high contrast image. But it could be very difficult in a low contrast image because you cannot identify a sharp intensity transition. Okay, so that's the idea. Okay, now how to do it? You have learned something from the morphology. To identify the edge, we can apply the first derivative or the second derivative, right? You call it a morphological gradient, right? The second derivative, we use a morphological what? Laplacian, okay? Morphological. So we have two choices. But for implementation, usually we simply go for the first derivative, because whenever we talk about the derivative, it can only be implemented in discrete image by difference. So if the first derivative is not stable enough, then second derivative is very sensitive to noise, okay? But that could be its advantage. Very sensitive to noise, which means, especially for a low contrast image, you might need to apply a second derivative to identify the hardly visible edges, but at the cost of noise. Okay, anyway, if we have an image like this, okay, suppose we have an image like this. In the central region is white, it's brighter compared is left and right regions. So if we would scan a line, horizontal line, we call it Y, the intensity could look like this, okay? It will look like this. Why it goes like this? I mean, ideally, for this, if we have an image like this, y. Right, we should have a signal like this, right? But in reality, it is not possible. You can take a very close look for any image. If you look for it, it's very close to it. In reality, it could go like something like this.
It's have a lot of noise.
Right. Yeah. It won't constant. Unless there's a very even you this a pure white strip on the pure background. But when you use the digital camera to capture the image, the graph value around here, okay, somewhere around here could be something, could be what? Let me make it larger. It's black, could be very close, could be only 10, and then 20, and then 30 something, and then getting brighter could be 150. You know what I'm saying? Then this could be 180, and then 200 something. Okay, so especially in the transaction. But let's assume we will steadily increase, okay, around the edges, and then decrease, then and go steady, okay, to the background. So if we have the signal like this, then we can take, this is line profile, then we take the very first, okay, derivative. We take the derivative of this signal. 微分，来看微分。The derivative for this point will be 0, 0, 0, 0, 0. What about this? The derivative is nothing but the slope, right? 斜率嘛, right? The slope is the first derivative. Then it's a constant. The slope will be a constant. So we have a point, something like this one. Okay? Within the object or the white strip, then the derivative again will become 0. Now, when we come to the right region, the slope will become negative, and it is a constant. So we have the magnitude here, okay? And then after that, the derivative becomes 0. Which means what? To identify the edges, we simply identify the magnitude. We don't need the sign. When I say magnitude, we for any value, okay, we simply take its absolute value. We don't care x is negative or positive. We care only about its magnitude. 中文就是我们只关心它的量，我们不关心它是正的还是负的，我们只关心它的量，它这个量够不够大。Okay, for this case, no matter it's a positive or negative, we care only about is if this magnitude is large enough, then we have a good evidence that this point got to be an edge. Okay, all others will have the magnitude very close to 0. Okay, now, so this is the first derivative. Now, let's look further. This is the second derivative. Second derivative is the first derivative of this signal. 这是延时影像的二阶，指的就是一阶的再一阶 ，right? The first derivative of the first derivative will be the second derivative. So again, we take the derivative for this signal. So everything becomes 0. Now, the derivative here will becomes what? Positive, because larger, and this is smaller. When I say derivative, we simply calculate the difference. That's it. We just calculate the difference. Okay? If we care about this one, the derivative is xi minus 1. That's it. Okay? We just calculate the difference. So this value will be positive, and this value, because this point minus this point, well, becomes negative. Okay? When you come to here, the derivative will be negative, because it's this point, the value of this point minus the previous point, right? And for that is this value minus this value, then it becomes positive. So it means what? If we use the second derivative to identify the edges, we use the sign. Because you see the sign changes here from positive to negative, or from negative to positive. Okay? But in real application, even you use the actually second derivative is based on Laplace. We still use magnitude, because if you just based on the sign, it will be very complicated. Why is so complicated? 4-dimensional, 1-dimensional is good. For 2-dimensional, what should be the direction you need to look for? You know what I'm saying? From positive to negative, or negative to positive. What should be then you need to check for all possible combination. If this positive become negative, or this positive and this negative. You know what I'm saying? I mean, it's getting complicated. So for real application, usually we simply go for the first derivative. If you need to use the second derivative, which is based on Laplacian, we still apply the magnitude. Okay, we don't actually look for it. Okay, so that's the basic theory. Okay, behind the edge detection, based on the first derivative, which is based on the gradient or based on the difference. Or we can base on the second derivative, okay, by using Laplace, okay, by using if you remember what I'm talking about Laplace when we talk about the smoothing, do you know what is the filter for Laplace? Anyone remember? Right? Laplace. Or, if you remember last week when we talked about the smoothing, or for 3x3, this is another filter, Laplacian filter, okay? So you can see the difference here, okay, right? That's a Laplacian. But we still use its magnitude. If we need to check its sign, I mean, the pattern will be too complicated, because you need to know which direction it will change the sign. Okay, so even you use a Laplacian, we still look for its magnitude, okay? Okay. Okay, so that's the idea, and then let's talk about how we implement or how we come up with the filter, okay, for edge detection. As I mentioned, if you go for the first derivative, okay, we simply calculate the gradient. As I mentioned, because our image is 2-dimensional, so the derivative is called gradient. We cannot call it derivative. When we call it gradient, which means if f of x, y is the original image, then we take the derivative with respect to x and with respect to y. That's it. Okay? So a gradient, actually, image processing, when we talk about the gradient, actually we mean the magnitude of the gradient. But actually, gradient is a vector. gradient is a vector. Whenever we talk about something about vector, it means we have two things. One is what? The length of the vector. The other one is what? The direction. The direction. 只要我们谈向量，向量一定有两个东西，一个是向量的长度，一个是向量的方向。Okay? So a vector provides the additional information other than the magnitude. It will give you also the direction. Okay, the direction. Where is the where? I mean. I know all this for this pentagon, and I know all these points are edges point, but their direction here, the gradient direction will be totally different. Okay? So it depends on your application. You might need this additional information to help you to make the judgment. Okay? For example, you care only about horizontal line, then you might need this information. But anyway, that's how we define the gradient. Okay, because we are talking about a two-dimensional image, so we take the derivative with respect to x and with respect to y, gx, gy. Then how to implement it in digital image? It goes like, okay, I'm sorry, here. Okay, the magnitude. Okay, the magnitude is nothing but the gx. Okay. The derivative with respect to x, we take a square, and the derivative with respect to y, we take the square, and then we take the square root, which means it's the length, right? This is the length of the vector, right? Here, okay? This is our g function. Then we have a gx. And then we have a gy. And also, you will have the angle. Now you know the angle. Dy over gx. Okay? Gy is the gradient. Okay? The gradient with respect to x. And this is the derivative with respect to y. Okay? And then we take gx. Then the length here. The length here is gx squared plus gy squared, then take the square root. Okay, this is the g. Okay, this is how we define it. But as I mentioned, you need to apply this. Okay, you need to apply a filter throughout every single point in the image, which means it's computationally very intensive. So if you don't care much about the details of the length, most of the case, we simply take the absolute value. It's much faster to calculate, and you won't hurt, okay, for real application, unless you need to know the exact length of this vector. Otherwise, this is much easier to calculate compared with, see that this you need to what? You need to take the square, and then take the square root. So if your image is 1K by 1K, you need to what? To make 1 million times of square and 1 million times of square root. Okay, even with the PC nowadays is still very fast, but this is even faster. Okay, because it does not involve any square or square root calculation. Okay, so it won't hurt the accuracy, just go for this one, okay? It's much easier for implementation. 直接取，就是我们直接取它的近似值就好，因为这样算起来会比较快， okay? They still represent the magnitude. So if this value is large enough, then it shows the evidence of an edge point for a pixel, okay? Otherwise, it could be just the background or somewhere inside the edges. Okay? And finally, you still need to apply something, you need to set up the threshold or use automatic thresholding, just like what you have done in assignment number 1. But the input is a gradient image. The input is a gradient image, okay? Then you need to find the threshold. If this value, if the magnitude is less than some threshold t, then you claim xy is an edge point, that's it, okay? Just like what you've done in assignment number 1. But for your assignment, for thresholding, the input is a grad level image. But for this one, the input is a gradient image. We call it gradient image, okay? This is the gradient image. No matter it's based on the square root or it's simply just take the absolute value, we call it the gradient image, okay? The gradient. The input is a gradient image. And still need a threshold. Still need a threshold. Or even you need to do some enhancement so that the difference can be visualized, okay? Especially for a very low contrast image. Okay, so everything will be the same, but the only difference is the input now is not a grad level image, but instead it's a gradient image. That's it, okay? That's it. Now, let's take a look about how we implement this operation, okay? This operation here in a digital image. The very first simple one is like this, okay? So, we need to calculate the gradient, okay, with respect to x. So, as I keep mentioning, the difference is nothing but the difference. So x plus delta x, you know what is delta x, right? In digital image, for your implementation. Delta x, what is the minimum unit in a digital image? 1 pixel, right? 1 pixel. So the minimum value, delta x, got to be 1, just 1, just 1. That's it, 1, 1. 所以呢，就有 x 加1, okay? X plus 1, 1. Okay, that's it. So if you have a signal like this, let me use one-dimensional case. Okay, so if this x and this x plus 1, then we calculate the difference, right? This is called slope, right? This is how we define the slope,
Yeah.
right? That's it.
Yeah.
So that's it. Delta x. For our case here, it is nothing but our slope is just x plus 1 y minus f of xy when we fix y, right? This is our x. That's it. And this is 1. So we change the 1. Y plus delta y, again, nothing, the delta y is 1. The minimum unit of an image, of a digital image is 1. Okay, it's quite easy to calculate the gradient, but it's not good enough, okay? It's not good. There's a lot of ways to define the gradient, okay? The other way around could be how to calculate the slope or the gradient. We could do something like this. Again, here is x. You might think of why not we take as to neighbor. It could be better, right? I mean, this one, we just look forward. This is called forward derivative. This so-called the centered derivative, which means we calculate then suppose we should be to delta x. Here, if the difference here is delta x, and this should be to delta x. Not set, okay? So we take this so-called the center. And this so-called the forward derivative. Of course, we can calculate backward. It doesn't matter, right? We can put this x and this x minus 1. It doesn't matter, okay? It doesn't matter. But anyway. Okay, that's another way. It could be better, okay? It could be better. Now, if we take this as a filter, 把它当成滤波器来看。Because we just think of one-dimensional, okay? We can extend it to two-dimensional. What should be the filter? Looks like. If this is x, this got to be x minus 1, and this x plus 1, right? So what should be the value here? Now, take a look here. If we take, no matter what, this is a constant, right? It's a constant, right? It's a constant. So we can drop it. So what should be the value? Did you see any f of x here? Did you see it? Yeah. No, there's no f of x, right? Which means is 0. What about s minus 1 here? So it's plus minus 1, right? Times, right? Right? So it's minus 1. What about s plus 1? It's 1 here. So it's 1. So that's how we design the filter. That's how we design the filter. This is the filter to identify what? Vertical line, right? See that? You need to move this filter, right? Pixel by pixel. So whenever there's a vertical line, it will show up right here, right? Because the magnitude is larger. Okay? So that's how we define it. What about the filter for? No, I should put y. The same here. Okay, so that will be the same here.
0.
Minus 1 and 1. It doesn't matter. It should be 1. If it's 1, then it got to be minus 1. It doesn't matter. Okay? That's it. Okay? So if this is y, this y minus 1, and this got to be y plus 1. That's it. And now we are going to extend it to this 1D, right? 1D filter. We are going to extend it to the filter with a 3x3. What can we do? We just repeat it, okay? Because for in a two-dimensional image, we just look for one dimension. It is too unstable. We prefer make it more stable, so that we just do the same thing here. We just repeat the pattern. See? So this is a 3x3 filter to identify the vertical direction. And we need another filter to identify.
Horizontal.
Right, very good. That's it. That's it. Okay? Or you prefer to put bias on the top, that'd be fine. It doesn't matter. And this is used to identify horizontal. And eventually, if we call this gx and call this gy, eventually you need to put gx squared plus gy squared and take the square root, or we simply take the absolute value gy plus gx plus gy. Okay, that's most of the case we apply it. Okay? So you need to filter, okay? One to identify the vertical line, one, I should not say, to identify, one to identify the derivative with respect to x. We find the gradient with respect to y, and then we put the magnitude together, okay? To make sure we have a high response for edges. Okay, that's how we get it. Okay, that's how we get it. Okay, so I can skip all this. I have just mentioned everything right here. Okay, so that's how we get. Okay, this is the GX. So we have the GX. Okay, the filter, and this is GY. Now, but I put a remark here. If you have the gradient like this, it says it's more sensitive to horizontal and vertical edges compared with diagonal edges. Because you can see, you just look for the vertical and horizontal. So if we have it means if we have an object like this, the response for the horizontal and vertical will larger compared with diagonal line here. Okay, you still can see a large response for the diagonal line, but it's not large as the vertical line and horizontal line. That's because it designs something like this. Okay? So just give me one more minute, then we can take a break. So to make the response will be equally the same for horizontal, vertical, and diagonal edges. Here, someone suggests, why don't we put 2 here? It makes sense, right? Why it makes sense? Because in terms of the distance, this 4 neighbor is much closer to the center. But for the 4 diagonal, take a look at the distance. The distance with respect, the distance is 1. There's 1 pixel, right? It's 1. What about the distance here?
2. 2 or...
If it's good, but right, that's right. But if it's a truly Euclidean distance, it got to be square root 2.
Square root 2.
Right, square root 2, right? It's 1 square plus 1 square, then take the square root. Right? So anyway, you're right. I mean, because square root 2 is not an integer. It's 1.41 or something. Okay, we prefer to take integer, right? So that's why. This is the final filter. And this is the most famous edge detector called sober operator. Everybody use it for edge detection. That's it. Okay. If you go for the OpenCV, this is the name you input. Okay. Not any line detection, blah, blah, blah. Okay, all line detection, you need to specify what operator you are going to use for line detection, and this is the most famous one. Okay, we take 2 for the 4 neighbor, and for the diagonal, we simply take 1. Okay, and the response will be better. Okay, for horizontal, vertical, and diagonal. Okay, let's take a break.